Hey everyone, my name is Chris, and we will be talking a little bit more about AI and machine learning today. This lecture will be the first lecture in a series of lectures related to AI, machine learning, and how that affects us as clinicians. The goal here is really not to turn each and every one of us into a machine learning engineer or a data scientist. The goal here is really to give us the tools to critique, review, and even use AI models that are being deployed in clinical practice today. So the main things that we'll cover today are 1, what machine learning actually is, 2, how do machines learn and what that really means, and 3, how do you judge whether or not you should trust the output of an AI model that you're using in clinical practice? And we'll talk about some of the things that can go wrong along the way. We talk a lot about machine learning and AI, and we talk about, oh, AI can do this and do that. But what is actually machine learning and AI? Well, machine learning simply is just using a computer to learn patterns from some pre-existing data to make predictions or take actions on new data in the future. And this is different from rules that we might write explicitly or algorithms that have step-by-step instructions. So let's take a step back. AI is an umbrella term, and it can mean a lot of different things. Expert systems, hard-coded rules, general intelligence, all of that. And within AI, we have a subset of that being machine learning. And the general idea behind machine learning is that a machine learning model can learn a pattern from data and apply that to new data it hasn't seen before. This is a little bit different from maybe some hard-coded rules we might be familiar with, like maybe a CHA2DS2-VASc score, helping us guide whether or not to start someone on AC or not. Machine learning models are less rigid, and the point is that they're able to take some input data and make a prediction based on the patterns they've learned. Now, even deeper within machine learning, there's something called deep learning, and that's a specific subset of tools within the machine learning realm using neural networks to do more sophisticated tasks. If you think about how Face ID works or AlphaGo works, those are specific complex models that have been built and used neural networks. And then obviously more recently, we've learned a little bit more about large language models. And those are the neural networks that sort of power these really fancy tools like ChatGPT, Claude, Gemini, and OpenEvidence that we've been using more regularly. So when we talk about machine learning, we talk sort of as like, oh, machine learning can solve any problem. But I think a more useful framework is to segment the tasks that we can solve with machine learning into different groups and the classes of different type of machine learning algorithms. So we have, first and foremost, supervised machine learning algorithms. And the idea behind a supervised algorithm is that it's trained on data that have specific labels. For example, let's say you have your email, you open up your email, and there's a lot of spam emails and there's a lot of good emails. In a supervised model, you would train a model on your email data where you have explicitly labeled, hey, this is a spam email versus, hey, this email is real, it's not a spam email. And the algorithm would have to determine based on the training data you've given it, whether or not any new emails coming in or spam or not. That is an example of supervised learning. Unsupervised learning is a little bit different. There's no explicit labels on the data that you're trying to classify or categorize. These clusters look similar. That means they must be similar types of data. If you've used Spotify, the online music platform, you'll realize that when you have a playlist and it might recommend you new songs, there's no real method to thumbs up a song. You can save songs, but there's no way to indicate to Spotify, oh, this is a song I like, and this is a song I don't like. So there's no labeled data. One way that they could be building out these recommendations for you is that they are essentially saying like, hey, you as person A seem to like rock or hip hop or whatever, and you like these songs from these artists. Well, there's another person who is very similar to you who happens to like also a lot of the same music as you. However, they've listened to this song and you haven't heard the song yet, so maybe we'll recommend that. That's an example of how you can use unsupervised learning to do things. And last but not least, there's reinforcement learning, where you don't necessarily tell the AI what's right or what's wrong, or the model what's right or what's wrong. You put it into an environment where the artificial intelligence can take actions and then it can get rewards or be punished for those actions. You're putting it in an environment that teaches it slowly over time what it should do and what it shouldn't do. Have you ever seen those YouTube videos where a video game learns how to play itself? That's the concept behind reinforcement learning. There's generally 4 big task types that we think about that we're trying to solve when we think about AI today. The first one being regression. So a regression task is something where you have some type of input data, and what you want to do is predict a number, right? So a good example of this is like, hey, given maybe the patient's vitals and lab values, can we predict their length of stay? That would be an example of a regression task because the output would be a number, which is number of days. Maybe can you predict when the next glucose value, or what the next glucose value will be at like 2 p.m.? That's another example of a regression problem that you try to solve with AI. A different type of problem completely is a classification task. So that's trying to categorize, based on this data, can we decide if something is in category A, B, or C? So maybe for a patient, given the same example here, you'd be like, hey, given the last set of vitals, what is the chance that they will be septic? That could be an example of a classification task. Or maybe given this image of a mass, can we define whether or not it's benign or malignant? That would be a classification task. Another separate task we can try to do with machine learning is detection or segmentation. An example of this would be like, given this X-ray, can we draw a bounding box around the nodule seen on the X-ray? Or maybe you give a clinical document and you say like, hey, given this clinical document of text, can we extract out the ICD-10 codes from it? That's an example of detection/segmentation. And last but not least, something we won't be talking as much about today, but we'll be talking about in future lectures, is generation. Essentially, can we produce new content based on some input data, whether that be a discharge note, a new image, etc. Now, those are the 4 different types of tasks. They can apply to any type of input data. For example, if we have tabular data like a patient's vitals, we might be able to try to do a classification task on whether or not they will be septic. A classification task on imaging would be slightly different. Maybe you give an X-ray of a patient's like chest X-ray, and then you'll ask the algorithm to predict whether or not this patient has pneumonia or classify whether they have pneumonia. You can apply this to text data. For example, let's say you give a voice transcript to this AI model, and the output of a classification task might be to decide whether or not this transcript is talking about whether the patient's trying to rebook an appointment, if it's a phone call, or if they're trying to call for a prescription refill. That's a classification task on text data. And last but not least, if we're trying to apply classification to signal data, maybe you're trying to apply it to an ECG and you're being like, hey, given this ECG, can we classify what type of arrhythmia this patient has? So as you can see, each task can apply to different type of input data types. And I want to talk a little bit about the life cycle of building a model, because we end up using a lot of these models that are deployed to us, but we don't always understand what goes into building a model in the first place. So the main thing that you normally try to do when you build a new AI model is you actually have to define the task. What are you trying to predict and why? You need to actually collect the data, decide what patients are going to be in your data set, if it's patient data, from where are you collecting this data, just your hospital versus multiple hospitals, and when, like what time span you're going to be collecting. You need to make sure that whatever you're trying to predict, the label is an accurate label. For example, if you're trying to predict blood glucose on a patient, like maybe predict the next blood glucose, are you going off the finger sticks? Are you going off the BMPs? What are you using as your labeled data? You obviously need data to train your model, but you also need data to test your model. And it's very important to keep those 2 things separate. Once you've actually built your model, how do you evaluate your model? How do you make sure that it performs well, not just on your experimental data, but when you deploy it, how it's going to do on when it's being used in clinical practice? Thresholds, where you decide to put thresholds, can matter. And then once you've actually done all of this and you've deployed it, how do you actually make sure your model is performing well in the real world? These are essentially, this is an entire life cycle of building a model and deploying it to production. So over the next few slides, I want to talk through a simple example of how we might train an AI model, just understand the process of what that looks like. So I made up this very arbitrary example here where we have data on patients. We have their height, we have their weight, and we have the resulting BMI. But for some reason, we've forgotten the formula for calculating BMI. Can we design an algorithm that if we give it the patient's height and patient's weight, it can predict what the BMI will be? So that's what this is saying. So this is a supervised task because we are giving the model labeled data to train on. The BMI is the output data we want to predict. So this is a regression task because it's trying to predict a number. The inputs would be the height and the weight of the patient. And once again, the output would be the BMI. So we're going to take a very simple example of a linear regression task. Now, this doesn't need AI, but we're going to be using an AI approach just for the sake of teaching. So a linear regression is something, as we all know, it's a straight line covered by the formula y is equal to mx plus b. The b is the y-intercept, the m is sort of the slope, and then x and y are like constants, right? The idea here is that when we draw a line, initially, it might be way off. It's going to be a random line. So this orange line represents our machine learning model. If we were to use this as is, it'd be highly inaccurate. As you can see, the data, or all the blue dots here, and our AI model as initiated is way off from that. So if we were to use this model to sort of guess what the BMI would be, it'd be highly incorrect. So how do we actually train our AI model to learn and be able to predict better? Well, there's a concept called gradient descent, or essentially minimizing a error function over time. And we essentially allow the model over many, many iterations and steps to try to minimize the residuals or the error between the training data and the model itself. So for this first iteration, we have all this training data. The model calculates the error between its reality and all the training data out there. And then it tries to minimize it. It takes a step toward the data. So in this case, it's taking a slight step toward the data, saying like, hey, the errors are pretty big here. Why don't we try to take a step in this direction and see if we can minimize the error? And as we see, when it does that, the error does minimize. The residuals get smaller. And we look on the right side on this graph, you can sort of see the loss, the MSE, is dropping with every iteration. And then over time, the model gets a perfect fit here because it's able to decrease that error function over time. And by the end of this, we have a line that perfectly fits our training data. So that's how like AI models might learn based on data. And that was a very simple example. Let's take a slightly less contrived example. Let's say that we have a set of patients with height and weight. So essentially they have the BMI. And then we're trying to correlate that with some non-deterministic outcome, like post-op complication severity. As you can imagine, that's not going to be as clean as a BMI calculation. So once again, this is a supervised task. It's a regression task because we're trying to predict some type of number, complication severity, which in this example, we're just going to make an arbitrary scale between 0 and 10. Input is once again the BMI, and the output is this complication severity. As we can sort of see, not every model is going to be a perfect fit for a linear regression task like we used in the previous example. If we draw a straight line through the data, yes, that technically fits this data at hand, but if you calculate the residuals, they'll be sort of large and there'll be some biases at either end of the data here. And it's going to be very hard to get a perfect fit. So complex data needs more complex models. So we could say, instead of using a linear regression, we could use maybe something like polynomial regression. But you do have to be careful that you don't overdo it, because the more you try to pick a perfect model and try to train too much, you could pick something that overfits the data. The point I'm trying to make here is that these machine learning models are sort of interchangeable. You can swap them in and out, like almost like you're swapping out the engine of a car based on the problem or the data at hand. And some other things are like decision trees. You could hypothetically use decision trees to help you do the same task. In this example, we've done forSplit to help us do that prediction. You could also use other models like something called a support vector regression or machine to help us draw a nice line to help us predict this data even better. Once again, just pointing out that there are multiple different machine learning algorithms that can help us with this task at hand. Another machine learning algorithm that we can use is something called a perceptron. And perceptrons are sort of interesting. Perceptron is the first step toward building a neural network. And we'll get to that next. But if we think about it, a neural network is just another algorithm and it uses a lot of the same approaches we've already seen. So the Lego piece of a neural network is a single perceptron. And you can think of a perceptron as like a neuron. In a neuron, there's a lot of inputs and there are outputs, and if we stack them together, we'll build a neural network. So what really makes up a perceptron? In a perceptron, once again, it takes some type of input. In this example, it takes a height, weight, and age, and it applies certain weights, or W1, W2, W3, sort of like little dials that you can tweak to say, hey, this is more important than that. Like height might be more important than weight in this algorithm. And these weights are learned through the training process. They get put through some activation function, which we don't need to go into, and then they spit out some type of outputs. In this model, what's being tweaked are the different weights, like W1, W2, W3, based on the training data. It can be used for regression or classification, and we're making some type of prediction here. So that's one specific perceptron. Now, the exciting stuff happens when you stack layers of perceptrons on each other to build a neural network. So in this specific example, we have an input layer, which could be height or weight, but I'm going to say it could be any data. We have these, what we call hidden layers, which are layers that don't directly spit out anything that we can see. And then there's some type of output layer, which is what we can see at the very end. So a very good example of how neural networks can outperform other models is with the MINCE dataset. Now, the MINCE dataset is a dataset that contains a bunch of handwritten numbers, like the number 8, number 7, number 6, etc. And the task at hand was, hey, given this handwritten 6, can we have a machine learning algorithm read the image data, process it, and then spit out, hey, it's number 6. With classical algorithms, this could be very difficult because you'd be like, oh, can we detect that there's a stroke here and then a circle here and that it connects together to make a 6? In order to sort of handle the real flexibility of handwriting, that would be very, very difficult. But using a neural network, this becomes a solved problem. So like a neural network like this, you can have the input be all the pixels of the image. The hidden layers over time, when you train the neural network, can learn different properties of the data set. Like, oh, maybe the first hidden layer learns how to detect edges. The second one learns how to detect strokes. The third one learns how to detect digit shapes. And the last layer might be just an output of like 0 to 9, and it spits out a digit. Each layer allows the neural network to learn a new abstraction or learn a new feature of the input data that allows it to predict an output. Our brains sort of do the same type of pattern recognition automatically. So this is like the first, it was really exciting because it allowed us to bridge the gap of more traditional algorithms to doing some of this fuzzy type of activities that we as humans can do. I think if this is something that you find really interesting and you just want to get into the nitty-gritty, a video on YouTube that's very helpful is something called But What is a Neural Network by YouTube channel 3 Blue 1 Brown. They do a lot of machine learning videos that I think are very helpful. So I want to take a step back. Where can machine learning models go wrong? When can they not perform as we expect them to? One concept is called overfitting. And essentially, it's what happens when you train a model based on some test data that doesn't generalize when you deploy it to the real world on real data. So let's look at this example here where we have a bunch of data points in the middle and we trained a machine learning model on this. So this is our machine learning model. It fits all of the points exactly. If you test it again on this training data, it would be essentially 100% accuracy. So it'd be fantastic. So I'm like, oh, why don't we take this model we've built that fits our training data perfectly and deploy it to the real world and see if it can predict the same way it does on the test set. So we now introduce a bunch of patients that the model has never seen before. And lo and behold, it performs terribly. So there's a concept called overfitting where essentially if you do too much training and you're not careful about how you train things, you can overfit on a few specific examples and then your model will not be generalizable. So how do we avoid this when building a machine learning model? So whenever you have any type of data that you're trying to train your model with, you should essentially have 3 splits of that data. You shouldn't take all your data and then train your model on all the data all the time, because you will never know that if you deploy it to the real world, how it will perform on real world data. So you can simplify this by saying just training data and test data. But if you really want to, you could do training data, validation data, and then a test set of data. And the idea here is that these are three separate data sets where a model being trained on the training data will never see the test data until it's time to truly test it. So that way, it's sort of like peeking at the answers. If you keep the test set outside, that can help you better understand how your model will perform on data it's never seen before, which can replicate the real world. And then if you're not careful, if you build a model that somehow incorporates the test data into its training set, when it comes time to deploy it to the real world, you might realize that, oh, my model in the real world is not performing as well as it did in my lab. So other things specifically to medicine that I think is pretty important is, let's say you're trying to build a clinical model based on some data you have. What are the splits that sort of matter? Now, it's not just about doing a test set and a training set, which is important, but you might have to think. An example I came across recently was, let's say we want to build a classification model, let's say like on EKG data on a patient. Do we want, and each patient might have like 50 EKGs. Do we really want that patient, when we split the data into training data and test data, do you want the same patient to exist in both the training set and the test set? There might be some properties of the EKGs of a patient that are very identifiable. And if you put that same patient in both the training set and the test set, you might overinflate your model's performance, and it might not be as generalizable to other data it hasn't seen before. Is that something to consider? So maybe you want each patient you're going to split by putting in just the training data set or the test data set. You can also further split things by a temporal split, like maybe train your model on data that only exists in 2020 and then test on 2023. And then I think it's really important, if you plan on deploying any models into the real world, especially if you're trying to deploy it past your health system, to make sure you validate your model on data it's never seen before, like maybe on a data set that was also provided from an external health system. One thing that is important that I'm not going to actually jump into is sort of like the numbers that papers sort of report when they're reporting on the performance of their models. Sometimes you might read something about like precision and recall, or like a F1 score. That's how some AI papers might report their model's accuracy. These might seem like new concepts, but they actually are concepts we already know. Precision is the same as positive predictive value. Recall is the same as sensitivity. An F1 score is just a unified score that combines positive predictive value and sensitivity together to give you a number between 0 and 1 to tell you how good a model is. And accuracy is just a proportion to correct. We all know that accuracy is not a great number to use, especially when we talk about like medical testing, because it can be influenced by lots of different things. As we know, positive predictive value is influenced by incidence. Okay, so let's say we built an AI model and it gives you a prediction. What do you do with that? A prediction is not a clinical decision on its own. You as a clinician still need to interpret it and figure out what to do with it. So when we deploy these AI models into the real world, it's not about building an AI model that has good numbers in the lab. It's about figuring out how it will impact you as a clinician when you deploy it to influence your decision and allow you to provide better care. So certain decisions when it comes to implementation should be: one, should this model work independently? Should it start taking actions on its own based on its decisions, or should it just flag cases for a clinician to review and take action on? Two, how does the model sort of fit into the existing workflow? Is it giving you the right information at the right time? Or, for example, if you have a sepsis AI model that's supposed to predict sepsis, is it telling you the data up front when the person first triggers SIRS? Or is it telling you 3 hours later after you've already fluid bolus the patient, given them antibiotics, and then maybe sent it to make you on pressors? And it's like, oh, by the way, your patient might have sepsis. So making sure you really integrate these models into clinical workflows is super important. It's not about just getting the right information. It's about getting it to the clinician at the right time. So I'm of the opinion that real world impact is actually more influenced by implementation of these models more than the performance of these models. But that's my personal bias. So talking about bias, I want to talk about a few case studies in the real world where AI models have been deployed in clinical settings and failed. So first story, this was published in 2019. where there was a widely used algorithm, the kind that decides who gets enrolled in extra care management programs that touched millions of patients. It was trained to predict a patient's future healthcare cost as a stand-in for how sick they were, which sounds reasonable. One thing they didn't realize until they deployed it much later was that Black patients were maybe being underrepresented in this, in the sense that, like, oh, Black patients were maybe being not counted as sick as their white counterparts, despite clinically still being quite as sick, but the AI algorithm was not detecting that. And then when they really dug through, it was because they had built a model that predicted essentially how much costs a patient would incur. And they didn't actually train a model to predict illness, which is what they were trying to do in the first place. In the real world, patients of a specific race might have less access. They might have barriers or utilize less care for one reason or another, whether that be structural barriers or maybe clinician biases. If we train a model on things like cost, we got to be careful about making sure that that's actually capturing what we're trying to measure. So if you're trying to measure illness, maybe using cost, and then training a model on cost might not actually get you there. In that initial paper, the authors were saying that if they had fixed the model to actually predict illness and not just the cost, it would raise the share of Black patients flagged for extra help from about 18% to 47%. It wasn't that the model was broken. The model was doing exactly what it was trained to do. It was just that the label they trained on, future cost, wasn't actually what they were trying to measure. They were truly trying to measure illness, and they should have used a better label for that. Story number 2 is this concept of shortcut learning, which I think is very funny. So back in 2018, there was a paper where they had published that they had built a model trained to detect pneumonia on chest x-rays. On their test set, from within its own hospital, it did really well. Their AUC was about like 0.93, but then they deployed their model at a new health system and it fell to 0.82. So what was interesting was that why was there a drop when they deployed their model that they built internally to a new health system? It turns out the model could tell which hospital an x-ray came from with about 99.9% accuracy because of other cues in the image, like the portable marker stamped up on the film, which was obviously ordered on more sick patients. And pneumonia was 34% of scans from one hospital compared to the other. So which hospital alone where these images were being generated from was enough to help predict whether or not there was pneumonia in the patient. The model essentially learned a shortcut, not the disease. It gave the right answer for the wrong reason, and that's the reason why that this model did not generalize when deployed to a new hospital. This is something that we call shortcut learning. And this is an issue that is very difficult to solve in clinical AI. And this is sort of what we've been talking about. Models can drop in accuracy the moment you deploy them somewhere new. That's why a lot of these failure modes, the harness, the data, the workflow, all of that matters. AI models can only be as good as the environment they've been built and deployed in. Other things I just want to quickly mention. We've already talked a little about workflow fit, where AI models have to fit into your existing workflow. Getting the right data at the wrong time makes any model useless. Automation bias. One thing that we'll talk a little bit more in the next presentation is that sometimes when a model spits something out, we just opt to trust it because, hey, an AI said it was good, it must be good. And then clinicians over time can learn to stop double checking the AI's work, and that can lead to issues as well. And something that we know very well already is alert fatigue. When we're building these AI models, are we building good models, but then implementing them in a way that makes them very noisy? For example, like sepsis alerts. Are they giving us the right information at the right time? Okay, and this, once again, this ties into what I was just talking about. How are we integrating these models within our existing workflows? So a few takeaways. A, whenever we're valuing a model, are we making sure that a model that performs well on its training data performs just as well when it sees new patients or new data? When you build a model, it's really important to make sure that you're measuring the right metric and that your metric is actually measuring what you expect it to. A model can be right for the wrong reason, just like we sort of discussed with the pneumonia example. Before trusting a model, we should really ask where the data came from, how it was validated, and whether it matches your clinical setting you're deploying it in. And a model may be perfect on paper, but how it's deployed, the harness around it, and Everything else really drives its real-world effectiveness, not just the model and how it performs on its research paper. So I'm not going to read this all around again because it's basically covering all the same things we've talked about. But here's a few questions you should ask for any model being deployed in a health system. All right, so that's part one. And in part two, we'll be talking a little bit more about large language models and AI agents.